Hi, and welcome back to Chapter 8, where we're covering earthquakes and some of the effects of earthquakes. In this segment, we'll talk briefly about earthquake frequency and magnitude. We've already discussed in the previous segment how we sort of estimate magnitude or the degree of shaking, what are some of the variables that are involved in that. And we've done that in a couple ways. Richter scale or Richter magnitude. I briefly spoke about the moment magnitude, and then finally the third version of this is the Mercalli scale, which is, of those three, it is the most subjective because it's how we experience earthquakes, and I'll try to relate those in this next segment. Then we'll also talk a little bit about earthquake hazards. Okay? So here's a good table to take a look at. Just ignore the table number here. It's not really relevant to your textbook, but you'll have something like this in there. On the left, we have Richter magnitudes. Remember, the Richter magnitude goes up to infinity, but we've never seen anything more than a 10. Actually, no, more than a 9.6. Here we've got the sort of qualitative description of what's going on. The Mercalli scale is also shown here. And then finally, expected number of seismic events of this size per year. So magnitude 2 is pretty small, and notice that here on the Mercalli scale, compared to the Richter scale, it's only measurable by instrumentation. So that means most size 2 earthquakes aren't going to be felt by us. But notice the expected annual number here is somewhere around 600,000 per year. As we go up in magnitude, let's say we jump to a 4, right? That's from a 2 to a 4. A 4 is 100 times stronger than a 2. Okay, and we see a Mercalli ranking of 4 to 5 and felt by most people, and only slight damage though. So sort of less than a 5, we're not going to get a lot of building damage. And then as we get higher up here into our 5s or 6s or 7s, we start to everyone feeling this kinds of seismic activity, but notice how many we have per year. So the frequency of these earthquakes goes down as the magnitude of earthquakes or the magnitude of earthquakes increases. And finally, we get here to a place where we call it major or total damage. A good example of some place that experienced major or total damage would have been Port-au-Prince, right? In 2009, I believe that earthquake occurred in the Caribbean, where we saw a significant amount of damage in Haiti and a massive relief effort, and that had a lot to do with both the building codes in the area and the economic or the infrastructure, which is in part supported by the economy of local areas. So if we take a look at magnitudes in Los Angeles or Japan, we can have kind of catastrophic events there, but we also find that very few people are killed, even though there's a lot of collateral damage, so buildings and roads and those sorts of things, which end up costing into the billions usually. If we take a look at this diagram, it's very informative. Here we are at a 2 on the left-hand side. In the center, we're going to expect, and this is a little bit different than the previous diagram, 600,000 to maybe even 1 million magnitude 2s per year. And if we go up here to a magnitude 9, sorry about that, I just covered this again. Let's erase that. Magnitude 9, we find we don't get very many of those, maybe 1 per year. On the left-hand side, we see some of the magnitudes. There's Kobe, or Kobe. There's Northridge, which is a quake I was around for in Los Angeles. And then on the right-hand side, we see kind of a ranking for the energy that's involved. And some of these are interesting. Atomic bomb, right, is pretty big, the amount of energy that's released, but we notice that there are many earthquakes that are much, much bigger than this. Volcanic eruptions actually contain a lot of energy in terms of explosive pounds is what they're really comparing this to. So a bomb, okay, pounds of TNT. That's how they're measuring the energy release. And so Krakatoa was a big volcanic eruption, and Mount St. Helens was also a pretty big one. And previously I told you, that nuclear bombs do send out seismic waves, and we can detect those. In fact, some of our early seismic networks were used to sort of monitor the behavior of pre-nuclear countries and to see who was doing testing and where that testing was going on. And today we're now using them to sort of limit nuclear proliferation and would be able to determine or evaluate seismic waves generated by a nuclear bomb, and maybe potentially locate the source of any kind of testing that's going on. Just a summary up here of cost of major earthquakes. Tohoku, that was recent. Here's Tahiti, also recent. 14 billion. Tohoku's in Japan, 300 billion. Kobe, 400 billion. Taiwan and India are a little bit less, depending on the seismicity, depending on the infrastructure in a community. It will dictate how expensive the earthquake is. Famous earthquakes, such as the San Francisco earthquake of 1906, were notorious for causing a lot of damage, in part because they led to fire. Fire is probably less of a problem today since we have a better fire suppressive construction, and we also have more sophisticated fire response or emergency response first responders. One of the important consequences of putting a building on the ground and building it in the right location is whether or not the ground is going to be stable during an earthquake event and seismic event. And liquefaction is a kind of a softening of the ground caused by seismic waves that pass through. So if you are uncertain of the construction and the footing under your building, it's possible that you could build it on clay. And the idea is that all the blue area in here is water, okay? And all these mineral grains or clay grains are held together by contact or points of contact. There's a point, there's a point, there's a surface of contact, a surface of contact. And so the force in here is a frictional force, right? It's a drag that's grain to grain. So when the grains are touching, the material is strong. And if this is filled with water, though, it is possible to shake this thing up and get the grains, because they're relatively light, to go in suspension. And so what we find is now when we have the seismic waves pass through, there's no grain-to-grain contact, there is no friction, and so that would allow buildings, as you see down here on the left, potentially entirely just to fall right over. And that's in fact what you have seen. The ground got soft, and the building, because it's top heavy relative to its footprint, it just basically fell over. Another hazard that we can have associated with earthquakes, and probably one of the most deadly, depending on where you are in the world, is the tsunami. The tsunami is caused by the displacement of the Earth's crust on the ocean floor. So if you have a seismic event in the interior of the continent, let's say near Chicago, you're not going to probably generate a tsunami somewhere else in one of the Earth's on the major oceans on the globe. But if you do have an ocean involved, what's really happening is that you're displacing all of this water and pushing it up a little bit. The actual amplitude on a tsunami wave is probably just a few meters, depending on where it is, especially if it's far from the coast. But as it gets closer to the coast, that amplitude will grow, and so it will get bigger and then bigger and then bigger, and finally wash up onto the shore. But it really has to do with displacing what could be 2 to 3 kilometers worth of water. Most ocean waves, just by comparison, are down here or up here, are just dealing with the first 100 meters of water or so. So ocean surface waves are in this area. So we're generating a lot of wave and a big energy to do it. And so in some places, what you'll see as the wave approaches the shore is that the water gets taken from the shoreline and sucked up into the wave. And so that means if you see a rapid retreat of the water along a shoreline, it's likely there aren't many other causes that there's a tsunami that is imminent. And the best choice for you is to find higher ground. I wanted to watch a couple short videos. What commonly happens with a tsunami is, you have the actual wave, and that's what they're showing here down in the bottom picture, which is a breaker, right? Here's another example of it. This is going to actually break on shore here. But what causes most of the damage is all of the flooding that goes on. And so the wave will flood inland for, let's say, 10 to 20 minutes and create a lot of damage. How fast is the wave moving? Can you get away from it? The answer is it's moving fast. 800 kilometers an hour in the open ocean is fast. And the best choice for you is to go up rather than to run inland. But heading up into a sturdy, tall building or some kind of stable skyscraper or structure. Alternatively, a large cliff would be good as well. So it'll just take me a minute to bring these up and oops, let me get out of here. There we go. Try this. There we go. All right. So just a couple examples of what it looks like when we have a tsunami that's active. So here, this is
northern Japan. They felt it. A violent magnitude 9.0 earthquake on March 11th, 2011. It was centered about 80 miles offshore, and tsunami warnings went up immediately. In coastal cities, people knew what to do next: run to higher ground. It's from these vantage points on hills and in tall buildings that incredible footage was captured. In Kesennuma, people retreated to a high-rise rooftop and could only watch in horror as tsunami waves inundated their city, knocking buildings into rubble and mixing into a kind of tsunami soup filled with vehicles, building parts, and contents. Seawater cascaded over sea walls and into cities. This video shows the water rushing over an 18-foot seawall in the Kamaishi city. The seawall here was the world's deepest and largest, but not enough for the magnitude of the March 11 disaster. It was the largest quake ever known in Japan, and one of the 5 largest recorded in the world. More than 28,000 people are confirmed dead or missing. When 2 tectonic plates push together under the sea, the resulting earthquake sends an enormous burst of energy up through the ocean, displacing enormous quantities of water. With the upward motion, a series of waves expands in all directions. In deep water, these waves travel fast, up to 500 miles an hour, but only reach a height of a few feet. A passing ship might not even notice. But as the waves enter shallow waters, friction with the ocean floor lowers the wave's speed, but raises their height. This video is from a Japan Coast Guard ship confronting a tsunami wave in shallow water on March 11th. And a rare view from the air, video of a tsunami wave approaching the shoreline. In Japan, some tsunami waves reach as far as 3 miles inland. Japan may be the most seismologically studied country in the world, and with more than 1,200 high-precision GPS stations, a geophysicist at the University of Alaska used the data to create a visualization of the March 11 quake. The waves of displacement that you see were moving as fast as 5 miles per second. In this photo, the ripples of tsunami waves are seen moving upstream in the Naka River at Hitachi Naka City. New technology left an enormous amount of visual evidence for study in years to come, and can perhaps help us better understand the power of earthquakes and tsunamis and prevent loss of life in the future.
All right, so that gives us an idea of sort of how devastating these kinds of tsunamis can be. In the case of the Java Sumatra earthquake that happened in 2004, we're talking about a loss of life, not just in the tens of thousands as it was in Tohoku, it was in the hundreds of thousands. And that has to do with the fact that Japan was actually ready for or had a warning system. And we have a warning system that's set up in the Pacific to tell us about the possibility of one of these tsunamis coming. But it turns out for the Java Sumatra earthquake, the epicenter was down here in this diagram in the bottom left. And if we look at where the epicenter was, it was somewhere in this area here. Wave height was about 60 feet, which is pretty tall. And wave propagation hit Sri Lanka and finally even the east coast of Africa. These contours show us where it was at different times. So time since the earthquake occurred here is 30 minutes, 2 hours, 5 hours, 7 hours, and the wave reaches the coast of Africa, but it's only a couple feet high at that point. How many people were killed? Hundreds of thousands of people were killed by the flooding and by the tsunami in both India, in Thailand, and in the Java, Sumatra region. Okay, they now have in the Indian Ocean a series of monitoring systems, kind of like those up here in the Pacific, which are called DART. And they have a kind of seafloor monitor because that's key. If the seafloor doesn't move, a tsunami is not going to be generated. But we also have a series of buoys. So we have to have something that comes up to the surface and then transmits that data into a satellite to help us sort of get the information off of the seafloor. And so we can use a surface buoy which can monitor upper level conditions of the ocean surface. Remember, the wavelength here is going to be very long for these waves, and so a very small increase with a long wavelength might be detectable at the ocean surface and give us some warning that a tsunami is going to come. The wave signature itself is unique, but also if you're in an area where you've got ocean crust that is moved, you also have a high potentially high danger for a tsunami to occur. So that wraps up for some of the common earthquake seismic hazards, and we'll move on to talk about the Earth's interior and the Mexico City earthquake in the next installments.